This is the third and final case for the characteristic polynomial. So before we had distinct real roots, we had a repeated real root, and the final case is imaginary roots. So it's easiest to explain this with an example. So let's go ahead and use our guess of y equals e to the rx and see what happens. So you plug that in, we calculate the characteristic polynomial, we'll end up with r squared plus 2r plus 2 times e to the rx equals 0. I don't know how to factor that in my head, so I'm going to have to use the quadratic formula. So in this case, we have a is equal to 1, b equals 2, and c equals 2. So if we do that, we have, negative b plus or minus square root, and let me make it a little cleaner, square root of b squared minus 4ac over 2a. All right, we'll start plugging things in. B is 2, so negative b, we get negative 2, plus or minus square root, we get 4, 2 squared, minus 4 times 1 times c is 2, whatever, and that's all over 2 times 1, so just 2. All right, well that ends up equaling, negative 2 plus or minus square root, we have 4 minus 8, so we have negative 4 over 2. Well, I can factor out a 4 out of the square root, so we have negative 2 plus or minus square root of 4 times the square root of negative 1 over 2. Right, so negative 2 plus or minus square root of 4 is 2. We're going to call the square root of negative 1 I, the imaginary number, and then that's all over 2. And if you simplify that, you get negative 1 plus or minus I. All right, and now we have a bit of a problem. So we have two solutions. Y1 equals the first root, e to the r1x, but that is e to the negative 1. I'll pick the plus I, it's the first root, times x. We also have y2 is e to the second root, r2x, but that's e to the negative 1 minus I, x. Now that looks a little weird because this is supposed to solve this differential equation, and the differential equation, doesn't have imaginary stuff in it. Let's just see what happens when we plug it in though. So if we take y1 double prime plus 2 times y1 prime plus 2y, we want to know what that equals. Well, okay, so to calculate the derivatives here, so every time we take a derivative, it drops down the derivative of the exponent, so it's negative 1 plus I times negative 1 plus I. So I'll put that here, negative 1 plus I squared times e, and negative 1 plus I x. So that's the y double prime term, and I've got plus 2 times the y prime term. Well, that's going to be dropping down the exponent once, so it's 2 times negative 1 plus I times e to the negative 1 plus I times x. Then the last term we get plus 2, e to the negative 1 plus I x. We still want to know what this equals. Now we got to go through and start multiplying. So in this one, this is going to be fun. So I'm going to definitely pull out the e to the negative 1 x, negative 1 plus I times x over here. So I'm going to worry about these. So if I square this, I get negative 1 times negative 1, so that's a positive 1. Then I have negative 1 times I, and then I'll also have another I times negative 1, so that's minus 2I. And then I have I squared, I times I, plus I times I. And then I'll have plus 2. This one's not so bad, so I can go ahead and write that out now. So I've got the 2 times the negative 1, so I actually have a minus 2. Then I have 2 times the positive I, so that's going to be plus 2I. Then over here, I just have my plus 2. And I had, said I was going to take out the common factor here, e to the negative 1 plus ix everywhere. All right, this last little bit, so we have this I squared we've got to deal with. So I squared, I equals square root of negative 1. So then if we have I squared, well, that's negative square root of negative 1 squared. So it ends up just becoming negative 1. The square root and the square cancel. And so this becomes 1 minus 2I and then plus I squared becomes minus 1. Then I have my minus 2 plus 2i plus 2, all times e to the negative 1 plus I times x. Well, here we go. We have a 1 here, we have a negative 1 there, so those are gone. And we have a negative 2 and a positive 2, so those are gone. We have a negative 2i plus 2i, those are gone. So this actually ends up being, 0 times e to the negative 1 plus I x. And that's what it's supposed to be, right? So this is 0, the right-hand side of the differential equation was 0. Even though this is e to a negative number times x, and the differential equation, doesn't have imaginary stuff in it, this does solve the differential equation. Unfortunately, though, it's got a pretty significant problem. So let me just block off an area here. The general solution would then be y of x equals c1 e to the negative 1 plus I x plus c2 e to the negative 1 minus I times x. We didn't explicitly, verify that the second solution solves the differential equation, but the same thing happens. You plug it in, you take the derivatives, you simplify everything, it ends up being 0. We've got this problem. We can't really work with this, right? How are we supposed to solve for initial value problems when we have exponentials with imaginary stuff in them? So it turns out you can actually solve this, or so you can write this in equivalent form. And I'll write here, so it's not the same c1, so I'm going to call this c1 hat times e to the negative x times cosine of x plus c2 hat, since c1 and c2 aren't the same as c1 hat and c2 hat, and it's e to the negative x again, and it's sine of x. The place that I got these from is this negative x here was the negative 1. That was the real part of the root. And then the value on the cosine x, this is 1 times x. Even though this is plus I and minus I, it's plus 1 times I, and this is minus 1 times I. So that's where the positive 1 came for the cosine x input. And yeah, that's it. So if you want to know how this works out, it relies on this cool formula, e to the I theta equals cosine theta plus I sine theta. And you can kind of rearrange terms to cancel out everything imaginary and just get this real stuff. That'll be a video at the end of this playlist. But otherwise, if you do end up solving for the complex roots, in this case it was negative 1 plus or minus I, by the way, it'll always be of that form. It'll always be something like lambda plus or minus mu I. Then you can end up writing out the actual solution that looks real instead of imaginary as this constant 1 times e to the negative x cosine x plus constant 2 times e to the negative x sine x. And we'll do some examples and go through and solve initial value problems, and hopefully you get some intuition on how to solve this and be able to do your homework.